Hi, I'm Candace Smith. I'm a technical sales manager here at RBR, for those of you who don't know me. And I don't know how to change my name, so I'm on the Zoom, so it's just RBR for now. Cool. So at RBR, we do, we measure the blue planet. So we do lots of different things, such as sensors, which like CTD, so conductivity, temperature, depth, and oxygen. This guy here is an oxygen sensor. We do loggers, which have battery and memory inside. So here we have, again, a CTD with a couple of cabled sensors on here. So it's powered and there's memory inside to pull all of the data into one platform. Then we do systems as well. So we use pieces of RBR equipment to integrate into larger systems, like, for example, the wire walker. And we also do what we call OEM, which is when we take parts of our sensors as well. So here you can see it's a CTD, and we configure them so they fit into other form factors for other manufacturers. So in this case, this is a CTD for a float manufacturer. In particular today, I just wanted to focus more on these like sensors and loggers, which is really in my background. So here at this end, here you see that we have two sensors. It's the dissolved oxygen sensor, and this is a temperature and depth sensor. So you can see these actually have connectors on the end here. So you would power them, and it's the way to get the data off all in one, from one connector. These next four white loggers here are our standard instruments. So they have batteries inside and memory inside, and these are all similar, but just slightly different. So here, again, this would be a CTD, and we have a couple of external ports for additional sensors, like on the last slide with like the dissolved oxygen. This is our Maestro, which can go up to 10 different sensors. So you have, for example, this one would have like CTD, and then you could add on chlorophyll or turbidity or almost any different type of sensors. You can see we have some connectors here on the back to add cabled sensors. This one's probably the most familiar to folks who use RBR for like profiling and open ocean work. It's a CTD, so it's similar to this one over here, is that this one just doesn't have the two connectors. And this is our littlest CTD. It's the Brevio. Instead of 8 batteries inside, it has 4. And you can see here, you can get versions where it has connectors on it to integrate into other systems. And just for scale, this is about 2 pop or soda or whatever you call it, cans tall. And finally, at the end here, this little yellow one is the Solo-T, the RBRsolo-T, which is what I'm going to focus on today. So all of RBR's compact series come in these yellow canisters like this. So in here is the battery and the memory, the electronics. And on the outside here, you can see there's this metal is the thermistor. So that's the thing that actually measures the temperature. And we have this red guard around. So this is a compact temperature logger. And as a reminder, that logger means it has memory and battery inside. For this flavor of the Solo-T, the fastest sampling rate is 2 Hertz. So that's sort of the regular sampling rate that comes with the logger. And if you record at 2 Hertz, you can get 25 million samples on just one AA battery. So 2 Hertz sampling is about 5 months of deployment. It's just shy of 5 months deployment. So that's 2 Hertz, that's 2 samples every second continuously. So every single second over that 5-month period. And if you sample slower, so let's say you want a longer deployment, you can sample at 5 seconds. So once every 5 seconds, and the battery will last for 6.6 years, which is a super long time. And no matter what sort of sampling regime you pick, if you get the 2 Hertz sampling, you don't have to sample at 2 Hertz. You can pick anywhere from 2 Hertz to 24 hours. And for those of you who are really familiar with Seabird's instruments, the Seabird 56, you'll know that these numbers are probably blowing your mind a little bit, because our endurance, it can be up to 5 times more, 5 times longer than the Seabirds. So our customers find a lot of value in that, because they can now maybe, instead of doing a 1-year deployment, they can get a 2-year deployment and have the same temporal resolution. The accuracy and the resolution of the Solo-T I've stated here. So it's 0.002 degrees Celsius accuracy. Sorry, I just like hovered over the resolution. There's lots of zeros after the decimal resolution. The stability per year is also the initial accuracy spec. So it's 0.002 degrees Celsius per year. And I think these specs and the accuracy and the resolution were crucial to Bernard's project, which we'll hear about very soon. Okay, so I'm just going to introduce a few different versions of the Solo-T, but before I do that, I just want to say, ask us for things. So ask us. We have a lot of different sensors, a lot of different configurations. Like if we don't make a sensor, we might integrate it from another manufacturer. Ask us what different depths you're going to and different regimes that you need. Like I need this in real time, or I need this on a mooring line, or whatever it is. Just always remember to ask us, because we know a lot about our instruments, obviously, and we can tell you, if you're trying to do this, we can point you in the right direction for the configuration. So I just wanted to mention that before I go into the details of all of these different versions, because there might be a version that you need that I'm not going to touch on, because it's, there's basically any combination of different sensors you can get. But for the Solo-T, so we have, this is the regular version. Shallow for us is 1,700 meters for this particular series, and it has a 1 second time constant thermistor. So this is it here, and this is the instrument that, like I said, Bernard is using in his research. So then we also have the RBRsolo³ Fast 8 or Fast 16 or 32. So that's just 8 hertz sampling, 16 hertz sampling, or 32 hertz sampling. And those have a 0.1 second time constant. So this Solo-T would look exactly like this one, except that this metal bit in here would be thinner, because it's a different type of thermistor, so it's a little bit thinner. Then you can also get deep versions. So our deep is 10,000 meters, so you get the Solo-T deep. So this is it here. So accuracy and resolution-wise, these guys are the same. They're just, this one just can go deeper. And again, the time constant is the same, of 1 second. And then you can get something that's a Solo-T fast and deep. So you can sort of get all the features in one. Again, this would be a thinner thermistor, and you can get, again, 8 hertz, 16 hertz, 32 hertz. And finally, I just wanted to bring attention to, so solo means 1, duet means 2, so you can also get a duet TD. So now, let's say you have some instruments on a mooring line, and you're expecting it's a dynamic environment, and things are maybe moving up and down or side to side, that having the depths or the pressure sensor, which is this guy right here, it might be really useful. And then you can get even more features like wave and tide data out of it. So our contact details are at the end of my part of the presentation. So if you have any questions, you can pop them in the chat now, or send us an email about any of these configurations. Okay, so let's look inside the Solo-T. So this was this morning. I opened up this one that I have right here. So again, for scale, you can kind of see it's like about the size of a cigar case, or a little bit bigger than my pen. So you just open it up here at the break between the plastics, the yellow and the red plastic. And inside we have a AA battery here. This is lithium. And we have some desiccant. So the desiccant is what keeps moisture from going on the electronics. So when you close up an instrument, there's moisture in the air, and then that moisture can turn into water droplets. So this desiccant soaks it up. This should be bright blue before deployment. Mine is white because I'm always opening up my Solo-T. It doesn't go in the water a whole lot. So just make sure before you deploy, this is bright blue. And it just shows the orientation of how the battery goes in. And then I just rotated it a little bit to show you where the USB-C connects. So this is a USB-C to a USB-A cable. So you just plug this end into here, and then you plug it into your computer, open up Ruskin, which is our software, and it will say, oh, hey, you're a Solo-T. And you can just, you can say, okay, I want to sample continuously at 2 hertz, or maybe you want to do 1 hertz, and you can change it, like I said before. You pick when you want it to start, so the day and the time. Maybe you want to do UTC, maybe you want to do local, and the clock on the inside the Solo will pick sort of whichever one that you choose. And then you can see here that I said that 2 hertz gives you about 5 months. So this is, essentially 3 days short of 5 months. And then when it's all set up, you just can hit this enable button down here. So it's like, okay, I'm going to turn on at 9 a.m. Today in this case. And one thing I wanted to point out is we have a lot of customers who use multiple solo Ts. So they'll set up arrays or many, under the ice, for example. So instead of going in and having to set up each one individually to say, sample continuously at 2 hertz, at this time, at this day with local clock, you can use this button down here. So you set up one, and then you plug in the next one, and you can pick use last setup. So it's a fast way to configure a whole bunch all at once, which is really, really nice. Finally, I just wanted to talk briefly about some RBR, some Solo T special pricing and lead times. So we do have quantity discounts on lots of our products, but the Solo T has its own special one. So it's the sort of 1 second shallow version, 1 second time constant shallow version. So it's 0.5% for every unit that you buy, starting for 2. So if you buy 2 units, you get 1%. If you buy 30 units, you get 15%. But it maxes out at 20%. So if you get 40 units or 50 units, it's still a 20% discount. A prepaid calibration voucher, if you've gotten a quote from us probably in the past year or year and a half, you would have noticed this as a potential option. So just in general, a prepaid calibration voucher is something you buy when you buy the instrument. It's good for 2 years. It includes return shipping. And as we recommend getting a calibration every year, it's a really great option. And there's usually a lot of cost savings. And for the Solo T in particular, again, it has its own sort of special pricing that the calibration voucher is less than $200 per unit, which is, that's not a lot in scientific dollars, I think. And finally, the lead time. So I did mention the lead times earlier, that our standard lead times are very quick, but you can actually get up to 50 Solo Ts in 4 weeks right now from us. So if after this, you're like, I definitely need 50 Solo Ts, we can get it to you in 4 weeks and a couple of days to get it for shipping. Cool. So, oh, right. Our next 2 webinars that are coming up, like I mentioned at the beginning, Anna Michelle and Rue Nicholson are going to talk about the Kenyak that they developed at Hui. And that's exactly 1 week from today. Again, 1 p.m. Or sorry, I said 1 p.m. Eastern. It's 12 Eastern. I'm in one other time zone over, sorry. So it's 12 Eastern. And in 2 weeks' time, Eric Oliver from Dalhousie University will be doing a webinar on some work that he's doing with community-based observations in the Arctic as well. So it's funny, they're both Arctic. So here are contact details. I'm just gonna leave that up for a sec. If you have any questions, and that's all the talking I want to do. And so, Bernard, I'd love to introduce you to everyone. That's okay? Yeah, okay, great, we can hear you. Okay, so can you tell us a little bit about your background, like how you got into these sorts of, your research, I guess?
Okay, yeah, so I'm right now, I guess I'm finishing on my 4th year of my PhD studies. I'm doing my PhD studies with Matthew Wells at University of Toronto, where we look at winter limnology. And I originally was a math major when I was an undergrad, but I was sort of interested in these environmental fluid dynamical problems. And so I ended up doing this summer research project with Matthew, and that's how, this is basically a continuation of that project. So that's how I ended up here, yeah.
That's awesome. I was also a math major. That's so fun. So what exactly did you do in this project? Like, how much were you involved? Did you go and do some deployments? Is it mostly the data work?
Yeah, I was involved in the deployment for, I think, 2 years. Because 1 year I was still completing my undergrad, so right. I wasn't able to do so. But I was out there helping with the deployment for 2 winters. And I think it was a lot of fun. It's a really great idea if you can just see what the actual deployments look like. Like for 1 year, I wasn't able to see what the actual deployments like. So it kind of wasn't as realistic, I suppose, when you can't see what's exactly happening.
Yeah, yeah. It's always nice to do it, to do the deployment yourself, because you have some sense of like the environment and what's going on there. So that's nice.
Yeah, exactly.
And before you get started, I have one last question. Can you tell us a fun fact about yourself?
Okay, well, maybe one of my favorite foods like curry, so I'm like really down to try a lot of varieties of them. I don't know if it's fun, but it's a fact.
Definitely fun. Food is always fun. that's, my, that's my mantra. Cool. So you can start sharing your screen. Hopefully everyone will be able to see it, and then they can stop listening to me.
So maybe I do this. So hopefully you can see this starting slide. Okay. So thank you everyone for tuning into this talk really. And Candace just gave us a really great overview of the RBR-Solo temperature loggers. So in this talk, I kind of wanted to show you an application where we use high frequency and high accuracy observations of mainly temperature, but also some dissolved oxygen to reveal the important thermal stratification and convection in ice-covered lakes. So in this talk, I'm basically going to first talk about the important physical processes happening in these ice-covered lakes. Then I'll try to explain why we actually need high frequency and high accuracy measurements to be able to resolve these important physical processes. And then lastly, I'll go into details of these interesting results we had from a 3-year field campaign. So the class of lakes that I'm going to talk about today are these ones called dimictic lakes. And these lakes are called dimictic because they fully mix twice per year. So once in the fall and once in the spring. And this happens because the thermal stratification in the lake is really weak. So when it's blowing on the lake, it can overcome that weak thermal stratification, cause the entire water column to mix. Now between fall and spring during winter, the air temperatures typically get really cold, so we have an ice sheet forming on top of the lake. And this effectively shields the lake from most of the wind effects. And the typical temperature profile during this period is an inverse thermal stratification, where it's really cold at the top, around 0 degrees, and then just slightly warmer at the bottom, at around 4 degrees or so. And I'll go into detail in the next couple of slides, what are the exact details during this winter period. But many lakes around the world can be classified as one of these dimictic lakes, because if you look at the countries with the most lakes, maybe Canada is one of them, as well as northern US, and many other countries in the northern Europe region like Sweden, Norway, as well as Russia. So we can almost say that most lakes in the world are actually seasonally ice covered. And the important thing that's really governing all these physical processes during winter is the freshwater equilibrium state. So what I'm plotting here is just temperature versus density of freshwater. And we can essentially see that freshwater has a temperature maximum density at around 4 degrees or so. Now in ice-covered lakes, typically we're looking at very cold temperatures between 0 and 4 degrees. And what that means is that if you heat up such a cold water body from above, then you're making the surface more dense. And that means you're making the water column gravitationally unstable. And this drives instability and convection. And conversely, if you heat up such a cold water column from the bottom, then the bottom becomes more dense. And that means you're stabilizing the water column. So this might be exactly the opposite you expect from summer seasons. But this has really important implications for what are the main physical processes during winter. And so on this slide over here, I'm just showing you a schematic of these main physical processes. And essentially winter period can be split into 2 periods, what we sort of call winter 1 and winter 2 in the literature. And on the left, I'm just showing you winter 1. This is sort of the early winter period where the air temperatures are really cold. And so you get thick snow and ice cover on top of the lake so that no solar radiation can penetrate through the ice down to the water column. And as I said before, the typical temperature profile is this inverse thermal stratification between 0 and 4 degrees. And during this period, you might get some sediment heating from the bottom or differential heating from the shallow regions of the lake that causes gravity currents to form. And that plunges down the side of the lake. Now, since you're heating from below, as I said before, you're stabilizing the water column. So what happens is that this inverse thermal stratification gets stronger over this winter 1 period. And this all happens until winter 2 on the right-hand side. So this is during the later winter where the air temperatures can go slightly above 0 degrees, so that the snow and ice cover actually partially melts and the ice turns from white ice into black ice. Now solar radiation is able to go through the ice and heat up the surface of the water column. And as I said before, heating up the surface is driving gravitational instability. And what that means is that this period is characterized by the development of a surface mixing layer. And this surface mixing layer actually deepens over time and erodes the inverse thermal stratification developed in the winter 1 period. Now, since there's also increased light during this period under the ice, we might also expect increased photosynthetic activity. So the dissolved oxygen will also increase in this convectively mixing layer. So these are really the main physical processes happening during this important winter period. Now let me just show you a little bit what the temperature profiles look like during this period. So what I'm just showing you here is some sample temperature profiles coming from our field campaign during this winter 1 and winter 2 period. So on the y-axis, I'm just showing you depth, x-axis showing you temperature. And the point of this picture is that the range of temperatures are actually really narrow during this winter period, so about 2 or 3 degrees or so. And if you look closely at maybe the winter 1 temperature profiles, the blue and the orange one, you can see that the vertical temperature difference between successive loggers is actually really small in some cases, can be less than 0.1 of a degree. And it's even less so for maybe the winter 2 profiles, the yellow one and the purple one. I think it might be a little bit hard to see on this graph, but the vertical temperature difference within the surface mixing layer, so that straight isothermal region, is actually less than 0.01 of a degree. And so that means that the magnitudes of the variability temperature is really small in these ice-covered lakes. But we'll see later that it's really important that we distinguish between these small temperature gradients in order to correctly quantify how much convection there is in the water column. And to correctly quantify how much convection there is in the water column, we use this so-called Thorpe scale method. And what this method essentially do is sort of a sorting algorithm acting on a measured temperature profile. So if you have a discretely measured temperature profile, maybe the one shown in the red dashed line, that may contain an overturn. So you see that you have warmer, more dense water over colder, less dense water. This method basically rearranges the profile back to a stable monotonic profile, so the blue curve below it. And in this process, it tracks how much each water parcel has to move vertically to be able to achieve this stable monotonic profile, and assigns a displacement to each water parcel, which is called the Thorpe displacement. And if you just take the root mean square of vertically of all these Thorpe displacement, you get this so-called Thorpe scale. So if the Thorpe scale is really large, that means the water parcel has to move vertically over a quite large range. And that means you have strong overturns and vigorous convection. And conversely, if the Thorpe scales are really close to 0, then basically the water column is already stable, and thus you have a stable profile, not much convection happening. And we use this Thorpe scale method because it's typically really hard to measure vertical velocities inside this convectively mixing layer, because physical scaling laws tells us that the velocities are typically on the order of millimeters per second, and that's quite close to the noise floor level of many current profilers. So that's why we use this temperature or density based methods. And so hopefully that gives you an idea of why we need high accuracy and high frequency measurements to be able to distinguish between these important features. And now let me just show you what our field site looks like. So our field site is in Lake Simcoe, and that's located in southern Canada around the Great Lakes region. On the top left over here, I'm just showing you a bathymetry plot of the lake. But our actual field site is located at that red dot over there. It's located in Kempenfeld Bay, and it has the deepest parts of Lake Simcoe, where the maximum depth is around 42 meters. And at that point, we essentially had an underwater mooring with a lot of these RBR-SO temperature loggers attached to it, so to give us a continuous measurement of temperature throughout the 3 entire winters. And so let's take a look at what the actual results are. So over here, I'm just showing you the results from a really cold winter of 2015. So on the top plot, I'm showing you air temperature. And what we can see is that it's a very severe winter. So most of the winter, the air temperatures are really below the freezing point. And then on the middle plot over here, I'm showing you the ice cover on the black line, and then the snow cover on the pink line. And then finally, on the last plot, I'm showing you the temperature time series we got from these RBR-SO temperature loggers. And the black line overlaying line on this plot is just showing you the estimated mixing layer. And basically what we can see is that maybe between February 1st and early March, before the orange dash line over here, you can see that the air temperatures are consistently below the freezing point, so that there's snow accumulating on top of the ice, and the ice is thickening. Now, if you look at the temperature time series in this corresponding period, you can see this inverse thermal stratification, where it's really cold, 0 degrees at the top, and slightly warmer at around 2 degrees near the bottom. And what we can see is that this stratified layer near the bottom is actually thickening over time. So you get heat accumulating at the bottom during this early winter period. So that's the winter 1 period. And then finally, if you go past that orange line, orange dash line, you can see that the air temperatures go slightly above the freezing point. And during this period, you can see the snow and ice cover start to rapidly melt. And what's important is in the temperature time series, you see this inverse thermal stratification being eroded by the surface mixing layer. So you see this surface mixing layer deepening and warming at the same time. And this all happens until the ice goes off when the spring overturn happens. So the whole water column starts to mix. And I just want to contrast this picture with another year. So this is the same spot, but just a warmer winter of 2016. And what you can see on the top plot of the air temperature is that there are several occasions during the middle of the winter where the air temperatures went above 0 degrees. And this has an important impact on the snow and ice cover. So you see the ice is much thinner and the snow cover is more patchy in this year. And then from the temperature time series, what we can see is that there's less heat accumulating at the bottom in this early winter of 2016. And there's also a shorter duration of winter 2 convection in this year. And furthermore, in this year, it's a little bit hard to distinguish between winter 1 and winter 2 as compared to the severe winter of 2015, where there's really a clear distinction between this winter 1 stratification period and the winter 2 convection period. So this gives us an idea of what the thermal structure is under the lake. And now let's try to apply this important Thorpe scale method to our temperature time series. So on the left here, I'm just showing you on the top the calculated Thorpe displacements for the 2015 winter data. So in this plot, any red color indicates a positive Thorpe displacement. So the water parcel has to move upwards to be able to achieve that stable profile. And conversely, a blue color just indicates a negative Thorpe displacement. So the water parcel has to move down to be able to achieve that stable profile. And then on the bottom, I'm just showing you the Thorpe scale. So if I just take the root mean square of the Thorpe displacement calculation, I just get that plot. And we can see that there's essentially 2 periods with elevated Thorpe scales. The first period is before February 1st. And that's when the ice cover hasn't become thick enough, or there isn't snow cover on top of the ice, so that solar radiation is still able to go through the ice and heat up the surface layer to cause convection. And then the second period is obviously this winter 2 period, where you get these increasing Thorpe displacements and steadily increasing Thorpe scales. So the convection is getting stronger over time during this winter 2 period. And then finally, between these 2 periods, you can see that the Thorpe displacements are essentially 0. The Thorpe scales are also really 0. So the water column is dominated by stratification, and this is this winter 1 stratified period. Now, if you look at the right-hand side of these plots, I just zoomed into the Thorpe scales during these increasing Thorpe scale period. And what we can see is that these Thorpe scales actually have sort of a diurnal pattern where it's maximum during daytime and minimum during nighttime. So this really suggests that the convection is driven by solar radiation. But we didn't have any light measurements during this year to overly confirm that, but we did have light measurements during the 2016 winter. So over here, I'm just showing you 2016 winter data. The top plot showing you air temperature, the middle plot showing you the measured under ice light, and then finally the last plot, I'm showing you the measured Thorpe scale. And essentially the story is contained within the highlighted panels, where in the highlighted panel, you see that the air temperature goes slightly above 0 degrees. And at that time, you might get ice and snow cover melting. So you have increased under ice light. And then that causes warming of the surface. So you get increased Thorpe scales, which means increased convective activities in the water column. And between these highlighted panels, we can see that the air temperatures are really low. And then so you might get a thickening ice cover, snow cover. So it's not much light. And consequently, there isn't much convection happening. So you see the low Thorpe scales in between these yellow panels. So this really suggests that these Thorpe scale measurements can help us quantify where and when the convection is happening. And also, together with the light measurements, tells us that these convection is really driven by solar radiation. Now, I just want to show you another application of these Thorpe displacement calculations is to try to connect it with is dissolved oxygen dynamics under the ice. So on the top two plots here, on the very top one, I'm just showing you the 2015 Thorpe displacement calculation. So this is the same as before. On the second plot, I'm showing you the dissolved oxygen saturation. So if it's a blue color over there, it just means low oxygen, while if it's closer to a white color, it's quite a high oxygen. And if it's red, that means the oxygen is super saturated under the ice. And on the bottom three plots, I'm showing you the same thing for 2016, except the middle plot is showing you the measured under ice measured light. And basically what we can see is that during this winter one stratification period beneath the mixing layer, we see that there's really no convection happening because of low Thorpe displacement. And consequently, because of maybe sediment oxygen demand or biological activity, the oxygen is actually decreasing beneath the surface mixing layer. But if we move on to look at winter two, where there's increased Thorpe displacement, we can also see that the oxygen is increasing within the surface mixing layer. And in 2015, we can see that the oxygen is actually super saturated. So this helps us give us this correlation between increased convection and increased dissolved oxygen, which may come from increased productivity because of the increased light. And so that's really the main point that I want to get across, is that winter can be separated into this winter one stratification period in early winter and the winter two convection period in late winter. And the point is that because we have such low variability of temperature during this period, we really need these high accuracy and high measurement and high frequency observation to be able to quantify how much convection there is. And that's really what the point of the RBRsolo temperature logger is, because it gives us a really high accuracy measurements. As Candace mentioned before, it goes down to maybe like 10 to minus 3 degree accuracy. And the bottom two papers is just me promoting myself. If you want to read more a detailed version of this talk, these are really the two papers to look at. Thanks.
Awesome. Thanks so much, Bernie. That was great. Do we have any questions? Anybody want to turn on their videos and ask some questions? There were no questions to come in through the chat. Oh.
Hi, this is Eric. I have a question.
Okay.
What is the smallest temperature difference that you saw that you think initiates convection?
So in this study, we essentially take twice the accuracy of the RBR-solo temperature loggers to say there's an inversion. So it's 2 times 10 to the minus 3 times 2. So maybe 4 times 10 to the minus 3 degree. And then we determine that to be an overturn. So that's what we apply to our calculations of the Thorpe displacement and scales.
Okay. Yes, and thank you. And I'll let Candace and you host a couple questions that have come in now.
Great. Thanks, Eric. So Jay asked, in winter too, it looked like the Thorpe scale never went to 0, even at night, question mark?
Yeah, so in these calculations, we did sort of a time average, because if you have so many, we're sampling at maybe 1 hertz or 2 hertz in some cases, you might get some sort of quite noisy data. So we did a time, like a running time average, about 3 hours or so. Another thing is that it might not like damp that quickly over the winter. I think the overturn could be continuing over nighttime. It just doesn't damp that quickly overnight. And then once daytime comes, this active convection initiates again. So during nighttime, it might not be active convection, but it might be just sort of not passive, but it's mixed. It's not mixing. That's the main point.
And we also had a question about time stamping. So were there time stamping issues on the mooring, or how did you line up the time stamps from the different instruments?
So for different instruments? I think, well, to align it, we just, as you said before, the software actually was pretty convenient. So we just did that to synchronize to the computer clock. And so the time drift wasn't that much, like a couple of seconds really. So I think they're quite well aligned.
That's great to hear.
I have a quick question. I was wondering about the spatial resolution of your thermistors, and if you could, I guess, give a guess of like the maximum distance that you could go to still see convection occurring.
Yeah, so in these field studies, our vertical resolution is typically like 2 meters, 2 or 3 meters or so. But if you want to go like a even better resolution, you can, because it really just dependent on the temperature inversions.
Yeah, yeah, I think those.
Jeremy asks, is there any lag between the maximum diurnal radiation and the maximum Thorpe scale?
There was some lag, like an hour or so, but it wasn't that significant, really, what we found that. So we might expect that the Thorpe scales start to increase maybe an hour or 2 hours after the sunrise, but I think on the grand scheme of things, it isn't that much.
Thanks.
We have another one. Has there been interest from water resource managers for this work to like predict algal blooms in low oxygen in areas, or something like on the snow level, the ice thickness, or something like that?
Yeah, I think if you look at this, hopefully I've just finished this final revision, so hopefully it'll come out soon, this L&O paper. And in this one, we really try to link these mixing and stratification with how much plankton there is throughout winter, and that can have an important consequence on maybe algal blooms later on. So hopefully this paper will come out. I don't know when they're finished. They're finishing their final proof.
Cool. Did you study the effect of plankton on Thorpe displacements?
Yeah, I think this might be hard to say, because what we found in another lake is that you get these diurnal migrations, I think is what that's called, for the plankton. But that you have to rely on sort of a current profile rather than temperature measurement. So I think it's a tough question to maybe answer with just temperature measurements alone.
Good day, Bernard. It's Bruce Hatcher here. Can you hear me?
Yeah.
Thanks for a very clear and interesting presentation. It helped me appreciate some of the complexity of the dynamics and some of the things I've been seeing in the system I've been working in, which is an estuary that has basins in it that are much lake-like, you know, as much as 50 meters deep, and quite isolated by the land boundary, although still connected to the estuary, often through shallow sills. My question for you is, if you introduce salt in significant concentrations to your system, let's say, you know, 20 PSU as an average, do you expect to see the same partitioning between your winter 1 and winter 2 patterns, and the same response of the system to the presence or absence of ice, or more generally, do you feel this model would work as well in explaining overturn and vertical structure in an estuarine system? Over.
I think this is a great question. I just wanted to have you look at this, maybe this winter 2 temperature profile over here that I sort of mentioned earlier in this talk, and you can see this unstable region where, I don't know if you can see my cursor.
No, I see it.
Yeah, okay, so you have warmer water or over colder water, and just based on temperature, this is really not a stable sort of profile. So this is possibly because of salinity stratification, because in Lake Simcoe, you have a major city around it, so these tend to have salt inputs into the lake. Mm-hmm. So we can still sort of infer this convection. Another thing is that if you have more like I think there are studies in like a lake in Alaska where they see salt stratification quite a bit. And what that just means is this convection layer might not reach the exact bottom. So maybe stay in the middle and then kind of disappear. So I think if you have significant salinity gradients, it would be better if you convert all of these into density. So if you have an equation of state, you can use temperature, salinity, but salinity, you might have to know the ionic composition. But if you use temperature, pressure, and salinity together, you can calculate the density, and then the same method really applies. Yeah.
Thank you for that. We sampled under the ice this year, and we have profile data. And we do also have some time series from multiple depths, although we certainly didn't achieve the the vertical spatial resolution that you did in your moorings. But I look forward to reading your papers, and thanks a lot.
Thanks.
Sorry, I'm just reading some comments in the, Jay put a comment there. Can you see that comment, Bernard? I was just wondering if you had anything to
I might need. Okay, so is it worth to put? Yeah, I think it might be worth it, because in that paper we studied, we only had like monthly averages of the plankton. So I don't know about the exact density calculations, but it's certainly helpful if you can see like a more real-time correlation between how much plankton there might be and the convection. I think that would be really useful.
Yeah, sorry, that question was about, just for the recording, that question was about if it was worth having chlorophyll as well. Does anyone else want to pop on video or audio to ask a question to Bernard?
How many? Oh, I might have to check my Excel sheet for this. But if we have 3 meter resolution, then typically each mooring we have. I think 2015 was the lowest resolution where we just have like 10 of these, 10 or like 12 of these. But in later ones, we fiddle around with the accuracy. I mean, the vertical resolution a little bit. So couldn't have more than 15, like 16 or 17 of these. Because 16 times 3 is like 48, which is like the maximum depth of the lake.
Cool. Well, if nobody has any more questions, I just want to thank Bernard for doing this. This is really great and super interesting. I want to thank the audience for coming and listening. And again, next week, Wednesday, it's 12 Eastern. Yeah, and I'm going to stop recording now. But then if you have any more questions or you want to pop on video to say hi, you can just go ahead and do that. So thank you, everyone. Thanks, Bernard.
Thanks.